free fatty acid and glycerol. So when C2 binds to LPL or lipoprotein lipase, it breaks down the triacylglyceride or triglyceride into free fatty acid and glycerol. So the free fatty acid takes itself into two peripheral tissues. The first one is our muscle. In this case, the skeletal muscle and the cardiac muscle. The skeletal and the cardiac muscle. Once the free fatty acid comes into the muscle, so we have our free fatty acid in the muscle, FFA. The free fatty acid is then converted into acetyl-CoA through a process called beta oxidation. Acetyl-CoA. So the free fatty acid is converted to acetyl-CoA through a process called beta oxidation. The acetyl-CoA finds itself going into the citric acid cycle or the Krebs cycle. The Krebs cycle now goes into the electron transport chain, where the electron transport chain makes ATP through oxidative phosphorylation. So the free fatty acid is being converted to acetyl-CoA through beta oxidation. Acetyl-CoA finds itself going into the citric acid cycle, takes it to the electron transport chain and makes ATP. Beautiful. The free fatty acid can also go into the adipose tissue. It can find itself, after the lipolytic pathway, finding itself in the adipose tissue. Once it's in the adipose tissue, it can react with glycerol to form what again? TAG, triacylglyceride or triglyceride. But mind you, do not mistake this glycerol for this glycerol. This glycerol is formed from glucose. There is a video I made where I explained hyperglycemia, that is high blood sugar. When the sugar in the body increases, when it's too much, beyond 80 to 120 milligram per DL, the beta cells in the islet of Langerhans produces insulin, which helps in yanking off or reducing the blood sugar or glucose into the normal range, which is 80 to 120 milligram per DL. Once it does so, the adipose tissue, it takes the glucose to the adipose tissue, where glucose is being converted to glycerol through a process called gluconeogenesis. When it does so, that is the glycerol that will react with free fatty acid to form triacylglyceride through blood transporters. So this glycerol is formed from glucose. This is different from this. I just want to make a distinctive difference between the glycerol here and this. So if you have not watched that video, I would advise you to go back and watch the video on hyperglycemia and the production of insulin. Good. After saying that, now I've done a lipolytic process where C2 bind with LPL, formed FFA, goes into the muscle. Through beta oxidation, FFA is converted to acetyl-CoA, goes into the Krebs cycle, goes to the ETC, which is electron transport chain, and forms ATP, which is used for energy. In this case, you are in an exercising stage. So what now happens? What remains from this particular metabolism? The chylomicron now finds itself going back to the liver. Going back to the liver. This is interesting. I am still saying this. You have to follow everything I'm saying. It's very important. So my chylomicron now goes back to the liver. So this is how the chylomicron will now look like after this lipolytic pathway, after this lipolytic process. So smaller than the way it used to. The triglyceride, I have some cholesterol and even some cholesterol esters. What is the protein associated with it? So now mind you, before it goes back to the liver, the HDL tells the chylomicron, hey, I want my protein back. So the chylomicron gives back the HDL its protein. What protein does it give it back? It gives it back C2. Protein C2, ApoC2. So what is left here is ApoE ApoE and ApoB48. So this is what's left of the chylomicron. This particular molecule is called chylomicron remnant. It's called chylomicron remnant. This is the remaining molecule that remains after this lipolytic pathway has occurred. So this is my chylomicron remnant. The ApoE has philia for a particular receptor found on the body of the liver. This receptor is called LDL receptor or LDL receptor related protein. Okay, so I'm calling this LDL receptor or LRP. LDL receptor or LDL receptor related protein. The B48 can also bind to something that is found on the body of the liver. What is it called? This is called heparin sulfate. So the B48s can bind to heparin sulfate so that the chylomicron can be taken into the liver for continuous breakdown of this triacylglyceride, cholesterol, and even cholesterol ester. So the ApoE has a high affinity for the binding of LDL receptor or LDL receptor related protein, while B48 binds to the heparin sulfate or the proteoglycans. Can also call them proteoglycan. Can also be called proteoglycan. Good. So once the chylomicron is taken in, now the chylomicron is inside the liver. The chylomicron is inside the liver. ApoE, mind you, once it's taken inside the liver, ApoE is a protein. Once it's taken inside the liver, ApoE is now synthesized to form amino acid. The cholesterol, the triglyceride is stored. What about the cholesterol? We haven't really touched the cholesterol. Well, the cholesterol can go into three phases. The cholesterol can go into three phases. Cholesterol. The first phase it can go to is the cholesterol can be converted to bile salt. This is the bile salt. So the bile salt can still go through the common hepatic ducts and still go back to the intestine and continue with continuously. So you see, the cholesterol can also be converted to bile salt. Where's our bile salt? This is our bile salt. Can be converted to bile salt. The cholesterol can also be converted because the liver can store it, but the liver does not store cholesterol as cholesterol, but cholesterol ester. So the cholesterol can be converted to cholesterol ester. So the liver saves cholesterol in form of cholesterol ester. Then how is the conversion? What happens? How is cholesterol converted to cholesterol ester? Through a special enzyme called acetyl-CoA cholesterol acyl transferase. Please, you need to know these things. So ACAT, that is the enzyme that catalyzes the reaction in which cholesterol is being converted to cholesterol esters. ACAT, acetyl-CoA cholesterol acyl transferase. This is the enzyme that is responsible for the conversion or converting cholesterol to cholesterol ester. So where does it go again? It can also go and form a portion of the cell membrane of the liver to give it its fluidity or rigidity. It can form here, it can come here and also form a part of the cell membrane. to give it fluidity and rigidity. So once this happens, there are other things that would occur. Mind you, we are not done yet. There are other things that might occur. I call this my common hepatic duct. Okay? There are other things that might occur. What will occur? The liver can also want to package the triacylglyceride and the cholesterol and even some cholesterol esters and send it back to the bloodstream. So what now happens? There is also a special organelle. Do not forget our special organelle, the rough endoplasmic reticulum. The rough endoplasmic reticulum produces another special protein, different from the one it produced when forming the chylomicron. What is that protein? So now let's say in the hepatocytes, we have my rough endoplasmic reticulum. It produces a protein called ApoB, in this case 100. Here we had B48. Now we are having B100. It produces B100. I told you the liver can also decide to package this. So what do we have? We have some triglyceride, some cholesterol, and even some cholesterol ester. What is associated with it? What protein is associated with this? I have what? What is the protein? B100. B100. So it can come back here. So now, let's say it's going back into the liver, it's taking it back into the blood stream. So we have it here. So I have my triglyceride, some cholesterol, and even some cholesterol esters. And what? B100. B100. What happens? The same substance or the same molecule that gave the chylomicron two proteins will also see this and say, hey, I would want to give you some protein so that you can continue your activity also. What is that molecule? HDL. HDL is so loving. So it gives it two distinctive protein. The first one is my ApoE, while the second one is ApoC2. So what we have here now is ApoE and ApoC2. This molecule is called VLDL, very low density lipoprotein. Very low density lipoprotein. What happens? This is not the end. This is just the beginning on lipoprotein metabolism. So I want you to have a bigger picture and understand where I'm coming from, and where I'm going, because it's much, but I'm really happy you're sticking with me throughout this video. So I'm going to take a little recap. So after forming my chylomicron remnant, it's been taken into the liver, connects with the LDL receptor or LDL receptor related protein. ApoE combines with it. It's being synthesized to form amino acid. The triacylglyceride is being stored. Cholesterol goes into three phases. One is the conversion of the cholesterol into bile salt. The other is the conversion of the cholesterol into cholesterol esters through the catalytic activity of the enzyme ACAT, which stands for acetyl-CoA cholesterol acyltransferase, that converts cholesterol to cholesterol ester. Why some of the cholesterol forms the cell membrane, which gives it its fluidity and rigidity. The B48 also binds with a proteoglycan, which is heparin sulfate. So the liver can also want to package the triacylglyceride, the cholesterol, and the cholesterol ester. But before doing so, The rough endoplasmic reticulum in the liver cell, produces a protein, a special protein called B100. When it goes back into the bloodstream, HDL, a high density lipoprotein, also gives it two distinctive protein, which is ApoE and ApoC2. That molecule that is formed is called VLDL. Are we there? Good. Very, very interesting. So the next thing we're going to do, we are still going to break down this VLDL and see what will happen. So you see this protein, this C2 protein. The C2 protein also sees this receptor. What is this receptor? This receptor is called lipoprotein lipase. So the C2 binds to lipoprotein lipase and breaks down and reduces the triacylglyceride. So what do I have now? When it breaks it down, so what do I have? When it binds to this, okay, when it breaks this down, I have some free fatty acid. When C2, okay, sorry, let me do it this way. Mind you, excuse me, so that I can have, this is called my VLDL, so that I can have space to connect the C2 to my lipoprotein lipase. So the C2 binds with lipoprotein lipase. So it breaks down the triacylglyceride or triglyceride to free fatty acid and glycerol or monoacylglyceride. So the free fatty acid can go into the muscle and still undergo these processes. That means when it goes into the muscle, free fatty acid is converted to acetyl-CoA, which is taken into the Krebs cycle or citric acid cycle, to the electron transport chain and forms ATP. So it can also branch and go to another peripheral tissue called the adipose tissue, where it combines with glycerol to form triacylglyceride. Beautiful. So when it does this, what do we have now? When it does this, now I'm going to go back so that we will move together. So